Okay, so this is the final question for our online tutorial. We have saturated steam at 180 m is discharged from a turbine at a rate of 1150 kg per hour. Superheated steam at 300 degrees C and 180 m is needed as a feed to a heat exchanger. To produce it, the turbine discharge stream is made with superheated steam available from the second source at 400 degrees C and 180 m. The mixing unit operates adiabatically. Calculate the amount of superheated steam at 300 degrees C produced and the required volumetric flow rate of the 400 degrees C steam. To answer this question, we need to really understand each information given in this question. Okay, first of all, we look at the first sentence. Okay, saturated steam. Okay, saturated steam at 180 m discharge from a turbine at a rate of 1150 kg per hour. So let's draw a diagram here. We have turbine. Okay, this is turbine. And then saturated steam is discharged from this turbine. So we have saturated steam at 180 m and the mass flow rate is 1150 kg per hour. Okay, this is the first condition. Next, superheated steam at 300 degrees C and 180 m is needed as a feed to a heat exchanger. Okay, to produce it, the turbine discharge stream is mixed with superheated steam available. Since it is not related to the turbine yet, so we just draw another flow diagram here. Okay, where we have heat exchanger. Okay, this is our heat exchanger. Then superheated steam at 300 degrees C and 180 m is needed as a feed. Okay, this one as a feed, superheated steam. So means we need to have feed to heat exchanger, and then this will be the condition: superheated steam. The condition is 300 degrees C and 180 m. Okay, then we have this term to produce it. In other words, to produce this second statement, the turbine discharge stream, which is this one, okay, turbine, is mixed with superheated steam available from a second source. Second source 400 degrees C, 180 m. Superheated steam. So in other words, we need to draw one more source here. Okay, and this source is superheated steam. Heated steam. And what is the condition? 400 degrees C and 180 m. Okay, mix here means this turbine mixed with this source. Okay, the second source. Okay, let's say this is the mixer. Okay, mix. The mixing unit operates adiabatically, means the Q is 0. Okay, adiabatically. And then what we need to do is we need to calculate the amount of superheated steam at 300 degrees C produced and the required volumetric flow rate of the 400 degrees C steam. So here we need to find the volumetric flow rate, and also the amount of superheated steam at 300 degrees C. Okay, the amount of superheated steam, which is this one here. So in other words, we only care for the part only. We don't care about turbine, we don't care about heat exchanger. So we just focus on this part. Okay, diagram properly. Okay, we have outlet from turbine here mixed with the second source. It will produce a feed for heat exchanger. Okay, this one go to heat exchanger. Okay, so this is the information that we have obtained just now. 1150 kilogram per hour. Okay, 1150 kilogram per hour. Then 180 amp saturated steam, and the same goes here. 400 degrees C, 400 degrees C, 180 amp. And then how do we get this enthalpy? 2676 kg per kg, kilojoule per kg, and also 3278 kilojoule per kg. As simple as we just check the steam table. Okay, and then one more thing, we need to find the volumetric flow rate, right? But before we find the volumetric flow rate, we can relate with the we can find the mass flow rate for this part. Since we have mass flow rate for this part, we have mass flow rate for this part, and also for this part, so we can have the mass balance first. Okay, so we have 1150 plus M1, because got two input, equals one output, so the output is M2. Okay, okay, now let's check how do we get the value of here. Okay, we go to the steam table where this is saturated steam, so we need to refer to table B.5. So 1 is equivalent to 1.0131 bar. So this will be the value for enthalpy for saturated steam at 100 degrees C and 1 bar. That's why we got 2676 kilojoule per kg here. Same goes for where we have 400 degrees C and 180 amp and the state is superheated steam. So you can check yourself the value of enthalpy where try to get this 3278 kilojoule per kg. If we combine everything that we have the mass balance just now. Okay, then we do energy balance. This is the open system, so this is the energy balance for open system. Q is 0 because adiabatic. Okay, this one is 0. No moving part. Delta EK and also delta EP. No no velocity, no elevation, so we only have delta H here equals 0. Okay, delta H equals 0. Okay, and like we have learned before, we need to factorize M. Okay, and then we use specific enthalpy for this part. Okay, because from the steam table we will get this value. This is from steam table, so we cannot directly get the value of enthalpy, but we just get the value of specific enthalpy table. And then we also learned before that we need to consider how many outlet and how many inlet. So in this case, delta H equals 0, but we need to take summation of outlet minus summation of inlet. So if we rearrange this part, what we will get is summation of outlet and H. Okay, this one is okay. How many component that we have? Then equals summation of inlet. Like shown in this part. Okay, here we have 2 inlet and 1 outlet. We already know the first inlet flow rate is 1150 kg per hour. If we go back to the slide, just here 1150, the first inlet. The second one we have M1, then the output we have M2. That's why here we have 1150 times with 2676 plus with M1, the second source, times with 3278 equals M2, the outlet, times with 3704. And I forgot to tell you that how to get this value. The same, we go to the steam table because this is superheated steam, so we need to refer table B.7. Since we already have 2 equations here, this is first equation, which is the total mass balance. Also, this is the second equation, okay, energy balance. So we can solve it simultaneously to get the value of M1 and M2. Now we need to find the value for volumetric flow for the source. If you go back to the flow chart, okay, we need to find the volumetric flow rate here. Okay, we already have the mass flow rate. Okay, what we need to do now is, okay, from table B.7, the specific volume of steam, okay, at 400 degrees and 180 or 1 bar is 3.11 meter cube per kg. So I will show you how to get this. Okay, this is 1 bar or 180 m. Then this is the specific volume. Okay, just now we got the value of n. Since we have the value of mass flow rate, which is this is M1, belong to the second source. Okay, then we have the specific volume at that operating temperature and pressure, which is 3.11 meter cube per kg. So we can cancel out the unit. Okay, then we get this value. So this will be the final answer, the final volume, the volumetric flow rate for second source. Then bear in mind, why don't we use density equals 1000 kg per meter cube here? Because the operating condition is superheated steam and the temperature is 400 and 180 m, which is not the same as 1000 kg per meter cube. Okay, this value is for liquid, not for superheated steam. Okay, so I hope you can understand all the explanation for online tutorial, question 1 till question 10. If you have any question or if you have any problem, please ask me. Go to the YouTube and make a comment or a lot of comments. It should be okay for me as well. I will try my best to answer your question. Okay, have a nice day. Thank you. Assalamualaikum warahmatullahi wabarakatuh.